maybe let's get started. So you may want to clone week 5. So we have some introduction to linear algebra. This is non-distributed linear algebra, mostly Scala briefs library. And then the next folder is on linear regression intro and distributed linear regression, linear algebra for linear regression introduction. So I'm going to heavily rely on some of the 2 or 3 of the videos from Amit's course. This is, remember, the second course in the edX series from last year. Just because I try to do it myself and there's no way I can do it more efficiently in 11 minutes. So I'm going to just rely on that, 2 videos there. And then this is the sort of bulk of it. This is the sort of 2016 machine learning library power plant pipeline. So we are essentially going to be spending more time on this. So remember, we already did step 1 through step 4 before when we did Spark SQL and data frames. So now we're going to do the other steps now: data preparation, modeling, tuning, and evaluation. We won't do deployment. So deployment is sort of the final icing on the cake. So I'll try and do that in the next 2 weeks. So deployment means you've sort of taken all this data, you've trained your model, you've tested across hyperparameters and validated the model across hyperparameters in that particular class. And then maybe you now compare more than one class of models, maybe linear regression and decision trees or gradient boosted ensemble methods, which we will do this time. And then you've chosen the best model out of that sort of model selection exercise across classes. And then now you're ready to deploy. So deploy means your power plant operator will want to actually be able to talk to the cloud and directly get feedback on what the power output is going to be in real time. So that's deployment. To understand deployment, I have to take you to the third component of the substack of Spark, which is basically the Spark streaming part of Spark. And so we will probably do Spark streaming next week. And once you understand Spark streaming, which essentially has windows to which stuff is streaming, so these are your queries from your power plant operator saying, hey, here are my environmental variables, what should be the power plant output? And then that streaming query will be processed through your learned model, and then those predictions will be served back. That's the deployment layer. So that's exactly the layer you will want to have in a recommendation engine for recommending apps to people about where they should go to date somebody or eat somewhere, whatever. So those are all the same sort of ideas. Okay, so we'll focus mainly on these. Okay, but before we can do that, we sort of have to get everyone on the same page about various things. So let's go to linear regression. So please make sure everyone is cloned and attached to one of the other clusters. So either the enrolled students or observing students cluster. Okay, so is everyone good? Okay. Now, those of you who have not had linear algebra or not done linear algebra for a while or sort of rusty, could you please raise your hands? No, right. Okay, so everyone's quite familiar with it. I definitely know there are people here who are not. So yeah, so it's okay. So we'll kind of try to cover it at sort of multiple levels, okay? So those of you who know a lot can get their hands dirty with more Breeze and Scala libraries for linear algebra. It's essentially C and Fortran under the hood anyway. And then the others can get some kind of geometric intuition for it. So it'll be like a strange 100, 200 level with 600 level mixed in, okay? Okay, so what's the plan? So we are going to use Amit Talwarkar's CS190.1x Scalable Machine Learning course. And so what we, so this is sort of homework, especially for those who are not familiar with Scala's numerical linear algebra package, right? So these are people who are typically used to MATLAB or Octave or PyLab. Or NumPy or whatever Python libraries. So then you can kind of look at this. In fact, this is then marked down and it's downstairs in the bottom of this worksheet. Okay. So what are we going to do? We're going to essentially learn about matrices, vectors, and doing arithmetic operations with vectors and matrices, and some kind of geometric interpretation of what these operations mean and these objects mean in just 2 and 3 dimensions. So, so before we do that, let me just take you through, so this goes back all the way to René Descartes. It was French, right? So Descartes came up with the Cartesian coordinates, right, to marry algebra and geometry. So that's kind of where I'm going. So what is, this is a very nice, it's called a visual cognitive tool, or so essentially we can interact. What I want you to pay attention to is A1 and A2. These are vectors right now, right? So A1 is this column vector, and A2 is just another column vector. See that these are 2 column vectors of this matrix A. So when I just move these vectors, I mean, don't worry about this thing right now. So I've just moved it, right? So now my A values are changing. This is 1 and, or that's A2. So A2 is now 0.78 to 0.48. So as I move this, you see this value, this column is changing. So a vector is nothing but a point in, say, 2 dimensions here. And A1 is just another vector, right? So this is the first column of the matrix A. See, it's changing. Okay. So that's essentially, so then when we have a whole bunch of vectors, we just put them as columns of a matrix and understand them as a picture of vectors. That's basically how we can understand a matrix. So later on, we'll see a couple more things. So if you take a vector and multiply it by a scalar, which is just some real value, then it just amounts to just stretching it if that real value is more than 1, or shrinking it if the real value is less than 1, or flipping it around. Oops, say visualization doesn't allow me to flip it and go back, okay? So if it's -1, then it just flips it on the other side. So those are scalar multiplications of vectors itself. And then if you want to take a matrix A and then multiply it by a vector V, right? So this is A times V. That's what this picture is trying to show you. I'll try to stay within the... So suppose this is A1 and A2, that's our matrix A. Then V, let's say V is this, this point here, 2, 3, right? So you can think of that as another line starting from the origin and ending up here. That's your vector V. Now what I'm interested in is A multiplied by V, right? So for my A here, these 2 vectors, A multiplied by V is A times V. And all that's basically doing is, essentially stretching A1 and A2 by V, and then finding the diagonal of this parallelogram and translating that. So if I'm blabbering, don't worry, it'll make sense as you start seeing examples and playing. So that's basically a matrix vector multiplication and geometric interpretation. Later on, we'll come back to this because we'll go into eigenvalues and eigenvectors, maybe for dimensionality reduction and principal component analysis. So just kind of have that floating in the back. Okay, so now I'm going to just play these tiny little videos because the math notation is quite nice, and we're going to stick to this.
A matrix is a 2-dimensional array. And we'll denote matrices via bold uppercase letters. For instance, the matrix that you see in the slide is denoted with a capital bold A. A sub ij denotes the entry in the ith row and j column of the matrix. So for instance, the first entry, the top left entry, is denoted as A11, and the entry in the third row and second column is denoted as A32. We say that a matrix with n rows and m columns is an n by n matrix. So for instance, the matrix in our example here, having 4 rows and 3 columns, is a 4 by 3 matrix. If the matrix is n by n, we also say that A is an R to the n times n. And we'll use these two notations interchangeably throughout the course.
Right, it's R because R is the set of real numbers, right? So, okay, so now we know what a matrix is. So what we do in Scala is we basically have to import this Breeze linear algebra package. Okay, so now we're able to do various linear algebraic computations, right? So once again, I wanted to remind those who are taking this for credit or paying for it, you have to get a grade. So the way the grade is going to be given is, you have to show that you've done some homework and understood the content. And the main part is the project you'll be doing. And for the project, you're going to be doing a presentation in the last 2 weeks of the course, right? So the idea is that your project is going to contribute to extra chapters in the course, right? In the Git book we're writing. So to be able to do that, how do you want to maybe convey some mathematical ideas, right? So if I double click this, you can see that Markdown actually incorporates LaTeX, which is this math notation. So math PF is math bold font A, begin P matrix is parenthetic matrix. So those of you who know LaTeX, most of you are taking the course for credit, know LaTeX. You'll know how to do this. So this is just LaTeX code. If you want to embed inline, you have to do / left parentheses, math BFA / close right parentheses, right? So these are essentially, you can so you can do very complex, you can prove theorems here and things like that. So, okay, so that's essentially a summary of what Amit was saying. Okay. So now let's create a matrix in Scala. So so val is again the immutable value A. We're going to use dense matrices throughout, but later on there's pointers to using sparse matrices as well. So now we just declare a dense matrix A to be the row 1, 2, 3, the second row to be 4, 5, 6. So this is a 2 by 3 matrix. You can ask what's the size of A, but before we even do that, let's actually hit tab and find out all the various operators and methods that are available for the instance of this object. There's quite a lot. Okay. Right. So this is kind of how I figure out syntax. And then I have to go dive into the docs. Okay, so A dot size, okay, it's 6. So what it's doing is basically representing the matrix as a one long, one-dimensional object, right? So you can ask what's the number of rows? That's 2. So clearly the size divided by the number of rows gives you the columns. Okay, this is basically how Scala Breeze deals with matrices. Okay, to access the element, this is the indexing begins from 0. So if you want to access the A11th element, right? Say in the math notation, the indices start at 1, then you have to do A00. This is like Python, but not like MATLAB. Okay, so it's pulled me 1 out, right? That's the first. So this is a gotcha, right? So indices in Breeze start at 0, so be careful. So now I can, of course, have a variable B. So if I have a variable B, I can reassign it, right? I cannot reassign to val. So val is immutable. So val is mutable. So that's what I've done here. I've reassigned it, and I'm getting my B to be something else, 9996 or whatever. So change some values here. Okay. So it's assignment, access, and modification. So let's look at vectors first.
Vector is a matrix with many rows and 1 column. We'll denote a vector by bold lowercase letters. So for instance, the vector in the slide is denoted with a lowercase bold A. A sub I denotes the ith entry of a vector. So for instance, A sub 2 denotes the second entry of the vector. If a vector is m-dimensional, then we say that A is an R to the n. In our example in the slide, A has 4 dimensions. So A is an R to the 4.
Okay. So that's in here. I'm not going to do this for every video. I'm just sort of setting it, So A is an R to the 4, right? So this is how you can do LaTeX within Markdown. Ooh, I made a boo-boo here, right? So I put math BF R to the M, which should be math BB, blackboard font. Sorry about this. Math BB. And
Last
yes,
one you corrected, you missed the curly bracket.
did I? Oh yeah, thanks. Yeah, that would not be good. It's all good? Okay, there we go. So now let's make a dense vector A, which is 3, 1, 6.3, and 3.6. This is from the video. And we can ask what's the size of A. And again, it's going to be 4. And we can ask the second element of A, which will be 1. So then we're going to look at the typecasting. So now we're going to actually explicitly say the dense vectors are type double. So now I can put integer strings here, 5, 4, minus 1. But because I explicitly said it should be double, it'll cast it as double. And of course, I can directly say 5.0, 4.0, and so on. And it'll then just infer the type to be double because of the 0.0. So do you guys remember this from first week, I think? Scalar crash course. Will this work? Remember MATLAB, if you just put 5 point, it'll actually infer it to be a decimal, but in Scala, it is not going to. You have to do 5.0. Okay. As it's a method operator. Okay, so now dense vector dot zeros double 5 is just a way to just quickly get a vector of zeros, and there's other things as well. You can do dense vector dot and then see a whole list of things. So this is just about transpose.
Next, let's talk about the transpose operation. In the transpose, we swap the rows and columns of the matrix. So for instance, imagine this input matrix here. Its transpose looks as follows. And as you can see, the first row on the left, 1, 4, becomes the first column of the matrix on the right. We can do something similar in the context of vectors as well. Let's talk about 2 different properties of matrix transposes. The first is that Aij, so the ij entry of A, equals the ji entry of its transpose. And we see this as follows. So A12 equals 4, and similarly, A transpose 21 equals 4. Second, if A is n times n, then A transpose is n times n. And so, for example, in the matrix examples here, the 3 by 2 matrix, when transposed, becomes a 2 by 3 matrix. And similarly, the 3 by 1 vector becomes a 1 by 3 vector. And both of these properties follow directly from the definition of a transpose.
So some of this may be boring for a lot of you, but this is sort of linear algebraically rusty people, right? So, and in fact, if I do some other kind of maths for a few months, I forget a lot of linear algebra, so I get rusty myself. So here's val A, dense matrix, 1, 4, 6, 1, 3, 5. So we can see this. It's a nice 2 by 3 matrix. I can do A dot T is the Scala breeze operator for the transpose. So let's just flip it around nicely. Val A is dense vector 3, 4, 1. And now I can ask what's the transpose of A, and it doesn't quite print it. It just says transpose of the dense vector. Okay, so here is addition and subtraction.
Next, let's talk about addition and subtraction of matrices and vectors. And these are element-wise operations. So for example, adding these 2 by 2 matrices, the first entry just equals 3 plus 4, which corresponds to the first entries of each of these matrices. The second one is 6 plus 8, and so on. Subtraction is the same, and here in the context of two vectors, to get the first entry, we just subtract 5 minus 4, and to get the second entry, we subtract 1 minus 4.
So you guys
It's important to note that matrices must have the same dimensions when performing addition and subtraction. So this following vector subtraction is perfectly appropriate because both vectors are two-dimensional. Similar, these two matrices are both 2 by 3, and therefore it's possible to perform the addition. In contrast, in this third example, the matrix on the left is 2 by 3, whereas the second matrix is 2 by 2. And therefore, this matrix addition is not possible.
Okay, so does everyone understand geometrically what vector addition is? Okay. So, you know, it should just be the diagonal of the parallelogram formed by the two sides of the parallelogram, where each side represents a vector. And in higher 3 dimensions, it'll be the diagonal of the parallelepiped, whose 3 sides are the 3 vectors. And beyond 3 dimensions, I don't know what it means, hyperparallelepiped. Okay, so it has some very nice geometric meaning. Okay, so that's the pop quiz. So when you take two matrices of the same dimension and add them, you know, you're basically doing this, you know, finding the diagonal of the parallelogram, you know, in this matched way. Okay.
If we currently define a matrix of int, does that mean if I do 2 large int sum together, that potentially can have overflow problem? Is it?
I don't know, overflow might be not castable. So
No,
yeah, if you add an int.
Yeah, it can be returning a wrong answer, or the actual functionality will check whether you over.
No, it's not. It's yeah, I don't think so. So there'll be So there's yeah. So maybe these are advanced topics for homework. So there's actually I completely confiscated and marked down the entire Scalable library. Silva's help. Also the quick guide, the cheat sheet that babbles between Python, Scala. What's the other one? MATLAB. So this is for the homework. So I think I highly recommend, especially those of you from Python, that will be very, very good too. And I'm learning Scala breeze myself. So
Yeah, it's kind of a little bit weird that you found metrics in int, because very likely you will, cannot do much computation and it will overflow the maximum user support.
yeah, I mean, I don't know what you can do. I mean, there's a chair professor who does computational number theory on modular fields of ints. I mean, okay, let's not go there. Right? So this is a different problem. So if you want to do multi-precision floating point arithmetic with Scala, there are ways to go with
What I
it.
was just wondering is when you do like a multiplication or any supported functionality on the dense matrix int,
Yeah,
if you over the maximum, like if you do minimum computation,
sure.
there is a check that you actually never over the maximum support or not.
No, it's not. No, it won't. Because even in week 2 in the Scala crash course, I can descend there now. I showed you, even when you multiply integers up to 21, it will crash, right?
Yeah.
So that's just, integers have limits.
So it doesn't really dynamically convert as Python do.
Dynamically convert from integers to doubles, or?
When you add the 2 integers together, if that's over the maximum support, it will cover through the automated transfer that the return to a floating. So you don't have to worry about that.
But you can easily overflow out of floats, right? Just 10 to the 308 is not. I mean, okay, we can discuss this offline.
Because this is statically typed.
Right.
So Python is interpreted language. So at runtime it will know the size of your variables.
Okay.
It can cast it. Scala is compiled already, so it cannot cast that.
So you have to cast it yourself. Yes.
Yeah, and that's the safety part of it. That's Darren Wilkinson's whole point about safety that Scala brings in, because it's type safe. You have to think about what you're doing. You can't just well. All right. So shall I continue? Because So let's just say we're just learning Scala, and this is all non-distributed linear algebra. So there's a whole worksheet on distributed linear algebra as well. Okay, so So I don't know, I'll just, so let's say A is this, and B is just minus A, just for fun, and then, you know, A plus B should be 0, and A minus B should be 2A, and whatever. Okay, so B minus A should be minus 2A. But you're welcome to play around. There are different you know, you have to make sure that the matrices you are passing in for arithmetic actually is of the right shape. Okay, or you have to write classes that do all this type, all this dimension checking for you, because you can actually not get errors if you say A minus B and A and B are not the right size, but you can actually get an answer out, but it will not be what you want. Right? That's the game, right? I mean, that's your problem. So if you go here, this is what I was, you know, saying. So if you, this is actually a linear algebra cheat sheet, and it's actually an extra resources linear algebra. And what this cheat sheet is essentially, it's from here. It's from the linear algebra, so the Scalar, natural language processing, Breeze libraries, linear algebra cheat sheet. Right? It's quite good. So what we've done is just wgot it with absolute links, and then use pandoc to mark down it, and then put the markdown pandoc after manual edits directly into this Databricks markdown, right? So the idea is it'll help you directly interact and learn. So I'm not going to go through all this, but you can see Breeze, MATLAB, NumPy, R, and what else is, yeah. So you can kind of see the syntax, and we haven't done all the details for you, so you can do dense matrix of zeros, double 2, 3 in Breeze, and you can do %pi import NumPy as NP and %pi NP.zeros to 3 in Python, or you can do %r mat.or.vec 2,3 to get the same object in R, right? So these are going to be processes that are running separately, and they won't talk to each other. If you want them to talk to each other, then I already showed you. If it's small enough, then you can do it through tables, right? Register temp tables. If it's really large, then you have to write to Parquet files, like we showed you in week 3 or something. Then those Parquet files can be read in as tables, or even though they're very large. And then you can babble the between languages, basically, through these tables. Okay, so there's indexing, slicing, and operations, some Boolean operations, various linear algebra functions, rounding, signs, and so on. Okay, it's a lot. Okay. So this is scalar multiplication. Let's look at what is dot product and matrix vector multiplication.
Next, let's talk about matrix scalar multiplication. And here, the idea is that we want to multiply each matrix element by a scalar value. So for example, here, we're multiplying each entry of this matrix by the scalar value 3. So the first entry becomes 9, the second one becomes 18, and so on. We can do the same thing with a vector and with a negative number as follows. Now let's talk about scalar products. And this is a function that maps two vectors to the scalar. So for instance, if we take as input these two three-dimensional vectors, the output, or the scalar product of these two three-dimensional vectors equals -9. How do we get these numbers? Well, to do so, we perform pairwise multiplication on the vector elements. So we first multiply their first entries, we then multiply their second entries, we then multiply their third entries, and we take the sum of these products, and we get -9. It's important to note that these two vectors must be of the same dimension, and also a scalar product is also called a dot product or an inner product, and we'll use this terminology interchangeably. More formally, matrix vector multiplication can be defined as follows. We start with a matrix A, and we want to multiply it by a vector W, and we get a result Y, which is also a vector. So how does this work? Well, consider the ith row of A, as well as the vector W. Then we can define yi, the output, as the scalar product between the ith row of A and the vector W. Moreover, we'll perform this operation for each row of A. So if A has n rows, and so then y is an n by 1 vector. Additionally, to perform the scalar product, remember that the two vectors have to have the same dimension. So the number of columns of A must equal the number of rows of W. Now that we've defined matrix vector products, we can revisit or reinterpret the scalar product as a special case of a matrix vector multiplication. And in particular, recall that we assume that vectors are always in column form, so that an n-dimensional vector can be represented as having many rows in one column, or that it's an n by 1 vector. And again, since scalar products require two matrices that are of the same dimension, x, if we're taking the scalar product between W and x, we also know that x is an n by 1 matrix, and therefore x transpose is a 1 by n matrix. And so as a result, we can think of the scalar product simply as the matrix as a product of x transpose W. And the output is y, which is a scalar product, which is n by n.
Okay, so you can also interpret this geometrically as an iterated Pythagorean rule, right? Depending on how you understand these things. So, and then you can see the scalar product as one coordinate of the accumulated diagonals of the parallelograms or whatever that you're iterating through. So a lot of those insights later on is helpful, you know, if you're really doing hardcore data science, you need a lot of geometric computation in 2, 3, and 4 dimensions to make sense of things. And I think we already went through this, so I think that was my point with just what is vector multiplication. So that's your matrix A now, it should be clear, and A times B is basically just a, you know. So now let's look at matrix A to be this dense matrix, 1, 4, 6, 1, 3, 5. And we're just stretching each column of A, right? So this will be 1, 6, 3 will be 1, 6, and 3. And then I stretch it by 5, right? So that's 5 times A. And A times 5 is the same. This is commutative. Okay. So, you know, so if you don't want ints and you want double, all you have to do is put double here, right? Then you'll be just in double land, and you know, it's good to stay in double land if that's what you want. Okay, now there's dot product. So A is dense matrix 1, 4, 6, 1, 3, 5, and B is dense matrix 3, 1, 2, 2, 1, 3. And then if you do A colon star, this is basically like MATLAB's dot star, right? So this is element-wise multiplication. So 1 times 3 is 3, and 4 times 1 is 4, and so on. 6 times 2 is 12, and 5 times 3 is 15. Okay, so matrix vector multiplication is again straightforward. We have A, and so this we can visualize as 1, 3, x is 1, y is 3, and x is 4, and y is 1. So these are the two vectors. If you want to see it in this column format. And then let little a be the dense vector 1, minus 1. So x is 1 and y is minus 1. And then you're just asking, you know, so A is just size 2. Now what is A times A? Capital A times little a. Then essentially the first guy gets stretched by 1, so he remains unchanged. That's 1, 3. And the second guy gets flipped to minus 4, minus 1. So 1, 3 plus minus 4 minus 1 should be minus 3, 2, right? Okay, so
next, let's consider matrix-matrix multiplication. This also involves several scalar products. And so let's start with an example. So here, we first take the first row of the matrix on the left and the first column of the matrix on the right, and we take its scalar product equals 28, and that gives us the first component of our resulting matrix. We then do the same thing with the second row of the matrix on the right, and that gives us the top right entry of our resulting matrix. If we then continue this process, we get the full result. So more generally, how does this work? Well, matrix-matrix multiplication involves two matrices, A times B, that we're multiplying by each other, and it returns the resulting matrix C. And so first consider the ith row of A and the jth column of B. Then Cij equals the scalar product of the ith row of A and the jth column. We'll repeat this process for each row of A. So if A has n rows, then so does C. And so that defines the number of rows of C. Next, as before, to perform the inner product, we must have matching dimensions. Therefore, the number of columns of A must equal the number of rows of B. And finally, we'll repeat this process for each column of B. So if B has P columns, then so does C. So in summary, matrix-matrix multiplication involves multiplying an n by n matrix by an m by p matrix and returning an n by p resulting matrix, where each entry of that resulting matrix is generated via a scalar product. Next, let's note two properties of matrix-matrix multiplication. The first being that it's an associative operation, or in other words, A times B quantity C equals A times quantity BC. However, it's not commutative, or in other words, in general, AB does not typically equal B times A.
So the associativity is something we take advantage of in matrices, right? Okay, so we just have a dense matrix, A and B, and we can definitely multiply this, right? So we get a 2 by 2 matrix. And we can check. So now what is the identity matrix? So this is.
Next, let's define the identity matrix. And to do so, let's think about what happens in the scalar setting. In the scalar setting, the number 1 is the scalar matrix identity. Or in other words, for any number C, if you multiply C times 1, you get back C. The identity matrix generalizes this idea in the context of matrices. So imagine that you have a matrix that's an n by n matrix, and if you multiply it on the left by the n-dimensional identity, you get back the matrix A. Similarly, if you multiply A on the right by the m-dimensional identity, you again get back the matrix A. Here's an example of the matrix identity in the three-dimensional setting. This is the 3 by 3 identity. And more generally, identity matrices are always square, with 1s on the diagonal entries and 0s elsewhere.
Okay, so that's essentially our unity. So here is A, and A times the identity is A, and the identity times A is also A. So note that I've done a 3 by 3 identity here and a 2 by 2 identity. Okay, so with the notion of identity, we can have a notion of the inverse.
Next, let's talk about the inverse matrix. And again, this idea is similar to what happens in the scalar setting. In the scalar setting, for any non-zero number C, 1 divided by C is the scalar inverse. Or in other words, C times 1 over C gives us 1. Something similar happens in the matrix M. And the idea here is that multiplying the matrix by its inverse results in the identity matrix. So imagine we have an n by n matrix A, and A to the negative 1 denotes its inverse, when it exists, and the inverse doesn't always exist. But when it does exist, A times A inverse equals A inverse times A, and both of those equal the identity matrix. And it's important to note that only a square matrix, i.e. those with the same number of rows and columns, can have an inverse.
Right, and again, inverses can be understood geometrically with the notion of signed volumes, right? So transformations of signed volumes. And so usually there's an object called a determinant, which involves the volume of the parallelepiped in 3 dimensions, for example. Okay, so now we have a dense matrix D, and D inverse, the val is just inv of D, that's the operator. So we got the inverse. And so D times D inverse should be the identity as you expect. So here it's all working in doubles. So I think this is the last one.
Finally, let's talk about Euclidean norms for vectors. And again, this is the generalization of absolute value in the scalar setting. So in the scalar setting, the absolute value equals the magnitude of length of a number. Similarly, vector rules generalize this idea for vectors. And the Euclidean norm can be defined as taking each component of the vector, squaring it, taking the sum of these squares, and taking the square root. And when n equals 1, or when we have a one-dimensional vector, the Euclidean norm equals the absolute value. Moreover, the Euclidean norm is related to the scalar product, in that the scalar product of a vector times itself equals the square of the Euclidean norm.
Okay, so I think that basically is all the sort of linear algebra square words we're going to need, okay, down the road. So I thought that's a good 11 minutes broken down, and you're also learning how to do Scalar in the same place, which you don't get to do in the edX course. Right? So I'm checking that norm of B is just 5, and that's just 16 plus 9 square root. 5. So this is what I already showed you. Please read this with a quick start. And the quick start itself is actually here in sort of partial markdown, right? So this is not the cheat sheet. The cheat sheet we've already done cleanly for you, but this is sort of the quick start guide. And if you want, you can start playing without. Please read this, right? So it's got a lot. So this is all, again, non-distributed linear algebra, right? This is your standard thing you learn. And so where to go next? This is just the HTML version. Sorry, I should have put another link here, but I already showed you the extra resources. Linear algebra has this already here. So. Oh, there's a really good news actually. So the Databricks guys, the Educate team of Databricks, is happy to prioritize people in the class here who are not enrolled students to give you guys accounts at the community edition. So I guess, yeah, so I will arrange for that. So for example, Steve and whoever, right, can get the Databricks Community Edition, which is independent of UC, and it's independent of the AWS grant we have for UC. So it's very powerful, well, relatively powerful 6-node cluster. You can do really fancy projects there, but you can do quite a lot there. You can do, relatively decent, scalable prototyping, proof of concepts. And who knows, if you're really ambitious, you can even pitch it to venture capitalists. So it's actually quite a good deal, because instead of being on the waiting list, Allison from Databricks, said we can do it. Okay, so I'm not going to, unfortunately, go through this. This is, again, like big O complexity, because we won't have time. But please do this. This is sort of homework. So you do need to watch the videos. I don't have time to show you because if you don't know complexities, time and space complexities, because we're going to build on that and bring in communication complexity on top of it. So, okay. If there's time, maybe we can go back to it, but I want to show you next least squares. This is our next stop in the machine learning world. So ordinary least squares. Once again, we'll go to this Berkeley visualization, interactive visualization site. So you can, again, adjust the scalar values by moving the points around and so on. Here's the basic idea of linear regression. I think they're trying to predict the height from the hand size. So there's like 1, 2, 3, 4, 5, 6, 7. Maybe this is Trump. Oh, maybe that's Trump, I don't know. So, so the idea is that hand size is possibly correlated with height. So here are your data points. And then this line here, this is basically our model, right? And this orange line is coming from this equation. 0.5 is the intercept, right? And this is the slope, right? This we call B1 or beta 1, or maybe beta 0, and this is the next beta value, the coefficient, it's also called slope. And then when you multiply that by the hand size value, you can predict the height, and that's the idea. So if I move this point, you're going to see the line changing, right? Because this is a best fitted line, and it's fitted using least squares, which essentially is for a given configuration of points, I just draw a straight line from each point, you know, drop it on the line here. So that'll be almost, let's say if I put this point right here, that'll be just along this grid. So that'll be the side of a square. And if I square it, that'll be a square sitting here, right? So that's the area of the square. So I sum the area of all the squares whose sides are what are called, what are they called, errors? Carl? What is residuals? Because they're sort of, so you take the sides and then you multiply it by itself, that's the area of the square, and then you sum all these squares, that's called the sort of sum of squares. And what you're trying to do is find beta 1 and beta 2 such that the sum of those squares is minimum, right? So if you think of it as an optimization problem, it's a minimization problem of the sum of the squared deviations between the data and the model, which is the straight line. Okay. Oh, sorry. So this is the picture I should have shown you. So if you just change, oh, this is not interactive. So yeah, this is essentially for the configuration of points, and this fitted line, this is the sum of the squares. So you can kind of add them and see what the error is and optimize there. So this is just showing it from different ways. So what the probabilistic interpretation is actually interesting as well. So what we can say is that this actually has a Gaussian error. So there's actually this true model. We can pretend this red line is the truth for a fixed parameter beta 1 and beta 2, and then these residuals we're seeing are actually Gaussian distributed noise around this straight line, which is your mean. Okay, so mean for the Gaussian. So you can just imagine lots of Gaussian sitting along, Gaussian density sitting along that ridge. Okay, and so these observations are seen as realizations of the Gaussian sitting on the line, and then the justification, the philosophical justification for this from axiomatic probability and stats is that we are essentially doing what's called a maximum likelihood estimate, which basically says for the given observation, what are the parameters beta 1 and beta 2 that are most likely to give rise to the observation I'm seeing, right? So that's the philosophical principle. A principle is asymptotically consistent, which means that as the number of data points go to infinity, my estimator, the way I'm doing this estimation process, will go to the truth, assuming there is a truth. Okay? So at least in simulations, you justify it, and that's essentially, yeah, so it's not just some heuristic optimization rule. There is actually some asymptotic considerations under the hood in probabilistic interpretation. Okay, so that's linear regression in a big hurry, right? So we're going to have to do it slightly more, slightly more formally. Otherwise, it's going to be more difficult to make sense.
In this segment, we'll talk about linear regression. We'll discuss its assumptions, formulation, and closed form solution. We'll also discuss a related model called ridge regression. Regression is a supervised learning problem. Starting with a labeled training set, our goal is to learn a mapping from featured observations to continuous labels. For instance, we might want to predict a person's shoe size given some other information such as height, gender, and weight. As another example, and this is a problem we'll focus on in this week's lab, we might want to predict a song's year given various audio features. Other examples include predicting power consumption of a computer cluster or predicting future stock prices. Regression is a very common problem in practice and has many applications. Now let's talk specifically about linear regression. And let's do this by using the previous example of predicting shoe size from 3 features, namely height, gender, and weight. We can represent each training observation via its numerical label, which we denote as y, and a 3-dimensional feature vector, x. Also, as a quick notational aside, recall that we assumed that all vectors are column vectors by default. And so in these slides, we're defining X transpose, where the transpose here is the T symbol. We're defining X transpose as a row vector, so that X itself is a column vector. Okay, so now our key assumption in linear regression is that there's a linear mapping between the features and the label. As shown in the equation, this means that we assume that we can define Y as a weighted sum of the features plus some offset value, denoted by W0. To account for this offset value, we can augment our feature vector by adding an additional feature that equals 1 for all observations. Once we do this, we can rewrite this linear mapping assumption as a scalar product. Specifically, in the equation below, when I equals 0, we are multiplying W0 by 1 just as before. It's natural to ask why we want to impose a linear relationship between the features and the label, as this assumption typically won't be correct in practice. However, using a linear mapping is attractive for several reasons. First, this assumption is intuitively and mathematically simple. Second, it often works well in practice. And third, when using this model, we have the flexibility to introduce new features as we like. So we can increase the complexity of this model via the process of feature extraction. Now let's get a better sense of what's happening by considering a simple example where we have a single feature as shown in the figure on the right of this slide. Here, each red point is a training observation, with its x-coordinate being its feature and its y-coordinate being its label. Our goal in linear regression is to find the line of best fit, or in other words, finding a line that minimizes the vertical distances between itself and all of the other training points, between itself and the training points. This line of best fit can be characterized by 2 parameters, namely its slope, denoted by W1, and its offset or intercept, denoted by W0. In the previous example, we wanted to find a line that minimized vertical distances. But more generally, we need to decide how to evaluate the predictions returned by our regression model. When doing so, it's important to note that in the regression setting, we can measure closeness between the label and the prediction. So for instance, when predicting shoe size, it's better to be off by 1 size than by many sizes, or when predicting a song year, it's better to be off by 1 year than by 2 decades. We need to pick a reasonable evaluation metric, or loss function, as we'll talk about, as we'll refer to it throughout these lectures, to perform this evaluation. 2 natural choices are absolute loss and squared loss, as they both incorporate this notion of closeness when comparing a label and a prediction. That said, the squared loss has some nice mathematical properties, and thus can be easier to work with. So we'll focus on it here. Now that we've described the assumptions of the linear model and picked the loss function, we're ready to talk about the process of learning a good model. Note here that we're defining a model via its parameter vector W. Let's further assume that we have n training points, where x superscript I denotes the ith training point. Our goal then is to find a model W that minimizes the squared loss over the training points, as shown in the equation on the slide. In particular, for a given data point x, note that the inner product between W and x is the model's prediction, denoted as y hat. Hence, for a given model W, we are computing y hat for each of the n training points, then computing the squared loss between y and y hat, and finally, taking the sum of these squared losses for all of the n training points. And our goal is to find the W that minimizes this summation. Next, let's rewrite this problem in matrix notation, as it's sometimes easier to work in matrix notation. We'll start, again as before, with n training points, and now we assume that we have d features. Given this data, we can first define the matrix X as an n by d matrix that stores all of the data points. We can also define Y as an n-dimensional vector storing the labels for our training points. Similarly, we can define y hat as an n-dimensional vector storing the predicted labels for our training points. And as before, we define w as the d-dimensional parameter vector or regression model that we want to learn. Note that the vector y hat is defined as the product between the matrix X and the model Y. To understand why this is the case, remember that the predicted label for a point X is the inner product between W and its features, lowercase x. And by definition of matrix vector multiplication, each component of y hat corresponds to one of these inner products. Now that we have this notation in place, we can define least squares regression via the following expression. In this equation, we're computing the squared Euclidean norm of the difference between two vectors y hat and y, which we can also, and we call this difference the residual vector. Note that this new equation is equivalent to the equation from the previous slide involving explicit summation. You can see this by looking at the definition of the Euclidean norm. For those of you less comfortable with matrix and vector notation, I'd encourage you to go through this exercise to prove to yourself that these two equations are in fact the same. So at this point, we've written down the optimization that we'd like to solve. And the next question is, how can we actually solve it? And it turns out that we can find the solution by taking the derivative of the function we're trying to minimize, setting it to 0, and solving for w. So to better understand this, let's see how this looks in a simplified one-dimensional case, where we assume that the offset equals 0. So in other words, in the example we're talking about, we're trying to learn the slope of a line that we know goes through the origin, or through the point 0, 0. First, we'll write out the function we're trying to minimize. Note that this is a function of w, where again w is the slope of the line that we're trying to learn. Next, by noting that this function is a summation, we can take a derivative by taking of the entire function by taking the derivative of each summand separately and then taking the sum. And the derivative of each of the summands we can compute via the chain rule. Once we have this derivative, we can set it equal to 0, and now we want to solve for w. In order to solve this equation, it can be helpful to rewrite it in vector notation. And we can do this by recalling the definition of the inner product. Once we've done that, we can divide both sides by 2, and we get the following equation on the right-hand side. Remember now that dot products are scalar values. So once we have this equation on the right, we can easily solve for w now, yielding a closed form solution for w. More generally, when dealing with many features, we can still obtain a closed form solution, which looks quite similar to the solution that we just derived in the 1D set. Moreover, although this solution assumes that the inverse of x transpose x exists, this assumption can be relaxed in practice. Okay, so at this point, we've covered the motivation, formulation, and closed form solution for linear regression. But one additional item to note is that so far in our discussion of linear regression, we've only been concerned with finding a model that fits the training data well, or in other words, that minimizes the squared loss on the training loss. However, our ultimate goal is to find a model that generalizes well, or in other words, makes good predictions on new data. Given that least squares regression minimizes only the training error, we run the risk of overfitting. So it would be preferable to solve a slightly different problem, and one that also accounts for the complexity of the different models and favors simpler models. Intuitively, models with smaller weights tend to be simpler, and this idea gives us a natural way to incorporate model complexity into our linear regression framework. With this idea in mind, we can revisit the linear regression framework that we've been discussing and introduce ridge regression. As with linear regression, ridge regression aims to minimize the squared loss between predictions and labels on the training data, or in other words, minimize the training error. But it also introduces a second term in the optimization problem, and the second term penalizes for model complexity. In other words, models with smaller weights will have smaller squared Euclidean norms, and thus all other things being equal, models with smaller weights will be selected over models with larger weights. Finally, Note that lambda in this equation is a free parameter that trades off between the importance of training error and the importance of the complexity term when choosing a good model. When lambda equals 0, we're back in the standard linear regression setting when we don't care about model complexity. In contrast, for very large values of lambda, we're prioritizing model complexity over training error.
Okay, so I tried very hard to do all of this in less than 11 minutes and 12 seconds, and it's not optimal. Okay, so this is much more optimal. So you've learned quite a lot here, right? So it's a very algorithmic approach, but there is a lot of probability under the hood, and I've given you lots of pointers in the notes to dive into it. The most important thing is ridge regression as one nice way to penalize for model complexity. And in fact, there is a nice probabilistic interpretation of it, which is essentially in section 7.5 of Murphy's machine learning book. So it's basically this book. And if you look at it, so what you can actually say is the parameters, the weights themselves, can be seen as coming from a Bayesian prior assumption where the weights have, are centered at 0. So if your prior assumption is that the weights, betas or W's or whatever, are centered at 0, then you are going to penalize weights that are too large, because in the Bayesian formulation, for those of you who know about it, we're multiplying the prior by the likelihood. So it's in the product. The maximum likelihood problem for that Bayesian model is ridge regression in this formulation. There are a couple other things you may want to be aware of, because this is one of the workhorses. So with linear regression, we can also have what are called basis function expansions. So you can have a sort of, the features can be x squared, and there's a feature x1, x2. It could be x1, x2, x1 squared, x2 squared, x1 times x2, and so on, right? So you can actually have functions of these features themselves as being your sort of new features, but then your weights are still going to interact linearly, so it's still a linear problem. And the nice thing about this ridge regression formulation is that it's what's called a convex programming problem. So everything is much simpler, because once you find the local optimum, it is the global optimum. Okay, so that's just a little bit more. So please, again, I already told you, start taking your own notes in your own clone worksheets. So for example, one sort of easy project would be just continuing along on one of these regressions, maybe doing something called lasso. So lasso is a L1 regularized method. It's very popular the last few years, and there are other regularization methods as well. So you can start exploring other things in the ML-lib, and maybe when you do a presentation at the end of the course, you can sort of find some videos. You can even make your own video and embed that video here. Okay, so I'm now going to do this. This is actually the million songs regression that is the case study example in this course. So we will do our own. Okay, we will do the machine learning pipelines using the power plant example, because that's a little bit more modern. Okay. Let's see. So how many of you know what gradient descent is? Okay, how many of you know what stochastic gradient descent is? So do you guys feel like watching this now, or do you want to watch it later, and then maybe we'll just spend a bit more time on the stuff that you can't watch? Because we can kind of abstract this away in the rest right now.
Or maybe later.
Yeah. Yeah, so let's maybe watch it later, because you can watch it later. But the idea is quite simple. So gradient descent, essentially what we want to do is have some update rules. So the slide basically shows that you want to propose new weights based, from the existing weights by essentially using the gradient, okay, and going along the path of the steepest descent. That's essentially the idea. And there are lots of variants of this, and it gets important what particular variant of gradient descent or stochastic gradient descent you use is going to depend on how large your n and d are. So d is the dimension, the number of features, and is the number of data points. And that's, that's basically there. So now let's get into distributed linear algebra. Okay, so once again, here's a reference. So this is a very brief paper, but the references and the appendices in this paper are very, very good. This is essentially this team, Mate, Reza, all these guys, MIT, Stanford, wherever they are, Berkeley. So this is quite quick, and it basically goes through the various ways in which you can represent matrices in a distributed way now. Okay, so basically a matrix, block matrix, and row matrix. And in the coordinate matrix, each non-zero entry is put in a separate RDD entry. In a block matrix, right, each block that's small enough to fit in memory goes into a single machine, and row matrix is, again, assumes each row is small enough to fit into memory, and it sort of has RDDs of rows. So, and then there's some explanation of what's really under the hood, and it's too bad one of our numerical experts left. So a lot of it is coming from some very old single machine code written in the 70s. So a lot of that is very useful now because you have lots of single core processes. Okay. So I'll let you read this, and I'll tell you where you can start getting your hands dirty in code. So if you go to the references here, okay, so it goes through optimization as well. And if you go down to the references, it tells you some of the core papers behind the various ideas. So you have to kind of dig a bit deeper. And then here's all the actual source codes from various places they're using. Okay, so this is some recommended reading. And then right here I've made, so again, this is a data bricksification of a good chunk of the machine learning programming guide. As I said, the programming guide is really big. But I've just done this for you, so you can go through the local vector, what's a label point, what's a local matrix. So we mostly have been seeing local matrices when we did the stuff earlier with Breeze. So now you can get into distributed matrices, and then actually there is three index row matrices, slight variant of row matrix, and then the three main matrices that I showed you in the paper that they're talking about. So this, so where do you go for this? So if you essentially go here, I guess. So there are essentially a lot of worksheets here. So you should be able to just, and I don't want to go through this myself because you're all grown-ups, right? So you can, yeah. And so you should be able to just shift enter and learn about, so it's abstracted away, so you don't have to worry about it. It's just there are many different ways of representing the matrices, but then you have to at least watch those videos to get a sense for it. And we're very quickly getting into a place where if you don't have the time or the energy, you shouldn't be working with these structures because they're very dangerous. They're all just RDDs. So you can do completely crazy wrong things, right? So the last worksheet is quickly taking you to this very nice la-la land again, where you can just do applied data science and process lots of data and let the engineers figure out how to actually lay the pipes and do the operations. Okay, but for those who want to do research, you really need to go through this, and we don't have time to go through this now. Okay. Okay, so here's a transcript of Amit's lecture, right? So he's basically nicely condensing what is distributed machine learning, what are the principles, and specifically what are these principles as they relate to computation and storage. Right? And once he goes through this, he essentially goes through another one, part 2, where he's talking about how to exploit sparsity in certain situations, how to minimize communication, and so on. So again, this is a transcript of it. So it's not a lot, but please try to understand this carefully. This I'm going to skip because we saw this already in the first week. This is just the communication hierarchy, and all it's saying is that there is a roughly 50 times gap between reading from memory, reading from either disk or the network. Right? So we have to be mindful of this communication hierarchy when we design our algorithms. And by design our algorithms, we're talking about doing everything from first principles, including how we define the scalar products that are under the hood for X transpose X operations, for example. So let me go to the so this thing essentially summarizes what are the basic rules of thumb. This is a very good 11-minute, 28-second video, and here are some strategies you need to focus on to reduce communication costs. So you access, essentially because the access rates fall sharply with distance. So now this is distance between the CPU and the memory and between different computers through the network and so on. We have to somehow be mindful of this communication hierarchy. Some elementary lessons are parallelism makes our computation faster, but network communication slows us down. So basically you want to perform parallel and in-memory computation, right? So we saw cache was a way to persist things in memory and distributed memory. And this is ideal for iterative algorithms, and most machine learning algorithms fall in this iterative family of algorithms, which is great. So gradient descent, for example, is in this family. So several machine learning algorithms are not just iterative, but also when you do training across various hyperparameters of that iterative model, then you can actually take advantage of parallelism again. This is also used to be called embarrassingly parallel. So there are ways of exploiting these levels of parallelism. Okay, so I'm just summarizing the video here. So it really depends. So if you have a big N, large number of data points, and a small D case, this is like for linear regression, this is like your sort of tall and skinny. So the matrix is tall because the number of data points is large, and it's skinny because the number of columns, the dimension D is small. So for that, you see each row will fit easily into locally. So then you want to exploit that basically. So all these big O asymptotics are coming from about 18 minutes of the previous video. So those of you who want to understand it, please go ahead and understand it. But we will quickly move to the application for now. Okay, so there's a difference again between the big N and big D case, the small N and the small D case, and so on. Of course, if anyone is interested in the mathematical asymptotic treatment of this for next year, I will redo Reza's course in full glorious detail, but I need at least 4 students if I'm still here. So it's a different problem. Right, but it'll be fun to do this. You have enough information in the videos there to actually start reading Reza's notes, I think. But this is, Reza's notes are the ones from the Stanford course, right? The third course we are trying to prepare you for. Okay, so now let's go into this worksheet. So of course now this is the Powerplan ML pipeline, right? So we actually are putting a very applied hat now. We're saying there's a business case, you have to make a living, we're going to whatever predict and serve some predictions to some clients, right? So it's a real problem. So once again, this is from week 3. What we're going to do now is just rerun steps 1 through 4. Remember, we did these steps for this Powerplan pipeline. Business understanding, loading data, exploring data, and visualizing data. So that's here, right? So this is actually a worksheet. So if I click and open, I can go here. So you may remember this from week 3, right? So the peaking power plant, blah, blah. So there are many ways to load this. One way is to simply do the following. Just run it. Okay, so now that whole worksheet is going to get loaded here. So that means all the objects there will be available here, right? So the data frames you're creating, blah, blah, blah. The other way to do it is to actually, go here and then run all, hit run all. But if you do this, the data frames you declare here won't be available there, right? Only the temporary table you registered here will be available there. So it depends on what you want to do. So I've done this. And then it just basically repeats the whole thing. Okay. So you remember we saw all of this and we said, oh, there's a negative correlation, but other, for one particular variable, but everything else looks kind of globby. And so, and then we loaded up this data frame with, atmospheric temperature, exhaust vacuum speed, atmospheric pressure, relative humidity, and what we are now trying to predict is power output. So these are the visualizations. So temperature versus power was very strong negative correlation, and others were not so strong. So this is the pairwise plot. So now we are going to do step 5, data preparation, step 6, modeling, step 7, tuning and evaluation. So in data preparation, let's just make sure that this power plant table exists, which is the one that was created in the other worksheet that we ran here. So it does. Here's my schema. It's all good. And this example, again, is nice because we didn't have any missing values and stuff. And shouldn't you miss the missing value thing? Sorry about it. All right, so now what we're going to do is call our vector assembler and turn these particular features or predictors into our input columns, and then set the output columns of the vector assembler to the string features. So now we have this thing called vectorizer, which takes the new instance of the vector assembler and will assemble the vector for us, basically. So now for data modeling, right, so here's my, here's actually what I'm trying to embed. Unfortunately, the LaTeX in the programming guide is not compatible with the Markdown or whatever, so we may have to go here directly. Okay. So this is basically linear regression in the MLlib programming guide. Okay. And what we sort of saw was ridge regression, which is one kind of regularization. But there's others as well, lasso for L1 regularization, and ordinary squares and so on. So of course, you can switch between, people know this, right? So Python or Scala or Java, just staying here. And it gives you examples of what's going on. And this is where I usually start from. Right? And then I think we may, have to go here for details. So this is actually the Scala API docs. Okay. And I'll try to answer Dominique's question from last week. The short answer is it's very difficult to embed these API docs within data frame notebook itself. It went through the Databricks support team the last couple of days, and it's actually a low-level problem with the Scala API doc people itself. Right? I can embed Python and Java, but not Scala, so it's kind of an unresolvable problem right now. But you can do the following. You can just right-click and go in. Then you can search here. So if you want to know predict, you can search here, and it'll bring up the different predicts. So probably, let's say you're interested in this predict, and it'll tell you something. Okay, so that's how you would, yeah.
I want to ask, for those machine learning that support the RDB, that means when you run the environment, you can change all the matrices online?
Yes, but the algorithms will be robust to the, so they will probably
Yeah, I know
assume
the
the
parameter
associativity.
selection problem is the same, but if you like to query the residual, the order of the residual can change.
Well, okay. So let's go down a little bit, right, and then we'll come back to that. That's a very low-level question. Let's come back to that in a minute. I'm just showing people right now how to find your way through docs, because you will have to find your own way through docs. Things change a lot. So we are actually going to be in Spark 2.0. That's why this whole course will not be very useful next semester. Okay, so it's kind of so yeah. Let me sort of quickly show you guys what the pipeline thing is, because it's quite different from the other two books I said from 2015, or also Amit's PySpark course from last year. So the first thing we want to do is split the data into a sort of holdout and validation set. Training and test set. So one way to do it is to just, we made this data set, right? We made this thing called the data set here, right? Which is just MySQL context.table. Remember, this will turn the data set. Data set is nothing now. There's nothing but a data frame, okay, from the table. So now let's split that data set using this random split function into 20%, 80%. So you have to pass in an array to say what fraction you want it to be. And then I'm passing in a long here because this is the seed of the pseudo-random number generator that will be used by this random split method, right? So it'll somehow split the data into 20% and 80%. And this is all IID assumptions. So now this is what I elaborated on. So Dominique wanted to know, can I quickly look at the syntax for each method like you can in MATLAB? So this is tricky for Scala, but it's possible for Python and Java right now. So these are called deep links, right? So we can't quite do deep links, and you can chase and find out why. And so the best thing I can do is to take the HTML, highlight it, mark down it, and put it here. But then I thought you can just do that easily by just chasing the URL. So for example, if you want to know about this method, right, random split, we know it's actually a method of data frame, right? So all you have to do is go to the API docs for data frame. So let's open in a new tab. So once you go here, then you should be able to search. So this gives you a very quick blurb about what data frame is, a quick example. And here you can search for random split, okay? So then you get the three possibilities. And I think you can see that from the signature of the input argument, I know this is a seed long array double, right? So it randomly splits this data frame with the provided weights. So I can just go here, get more detail, and so how do you drop into the source code? Do you know?
So there's a source at the top.
Here?
Slightly more. There's a source. Yeah, right there. It's the publisher. Data frame of Scalar.
Oh yeah. Okay, cool. So so if you go here, then I mean, this is the reason we're not doing MATLAB, right? So the whole planet can contribute to what you want to do. So there we go. So we are in GitHub now. So this is basically where you have to go to find answers, right? So I won't simply be physically able to find answers for every question because it's massive. Yeah. So I hope that was helpful. So now what I'm going to do is have a train set and a test set and a training set. The split 20 was my data frame I just made, right? And split 80 is the other one. So I'm going to call my split 20 train set and my split 80, test set and train set. I'm going to cache it because I'm going to reuse it. So then if you want, I can just look at the top three and see how it looks. So I can see that these are just arrays. Okay, so So now here's my linear regression model, right? So I import linear regression model and pipeline, and then I have a val LR, which is a new linear regression model. So now what I'm going to do is LR.explain params. So this gives me all the parameters that are set right now. So if you ask what is the linear regression model doing, then this is a one way to find out without going crazy too quickly, right? So there's an elastic mixing parameter. That's again another penalty technique. Penalty is an L2 penalty for alpha equals 0. For alpha equals 1, it's L1 penalties. Default is 0. So we are in L2 penalty, which from the video is sort of regression, right? I believe. Okay, so, and I just figured it out right now reading it. Right? So feature columns is here. Well, max iter is actually default is 100. This is the number of iterations that you have to do in the gradient descent. For example, okay, and then the solver for optimization. This is actually auto, right? So what they've done now is they try to figure out which optimization algorithm is actually ideal for your problem. So this is a lot of heuristics that goes into making this decision. Whether if your data is very small, then they will actually just use a method that's going to work on each worker directly. If it's a small n and large d, it'll be different, and if it's large n and small d, it'll be different, and so on. So those decisions are already made for you. That's why I sort of quickly brought you here. Right? If you want to really understand that process, you have to look at the other videos and take your time. Okay. Okay, so now the next thing we're going to basically do is set the parameters for the method. So I'm going to say set prediction column to predicted power output, set label column to PE. I'm going to use my max iter to be 100. Of course, you can change the defaults here. And now I'm setting the regularization parameter to be 0.1. So this is going to be so it's going to be somewhere between these two. Okay, so now the LR pipeline is going to be new pipeline, and then I'm doing my set stages. So remember, in the pipeline, I set the stages, and I have to put each stage of my pipeline. So I in an array. So I first do the vectorizer, then I pass it the linear regression, this model itself. So now my LR model is simply, I take the pipeline and just call the dot fit method to the training set. So that's it, right? So this, and just briefly, I have Y to be B0, B1, X1, B2, X2, B3, X3. I think we just have B4, X4 in this example, only 4 features, right? So my BIs are my coefficients and B0 is my intercept. So my fit has completed. And now I just have to do find my intercept. So for intercept, I do LR model stages of 1 as instance of linear regression model.intercept. Right? So if I do this, I get my intercept to be the double 439. And then for coefficients, I just do the following, right? So once again, stages 1 as instance of coefficients, and then I convert it to an array. So I get the array of coefficients. But now I don't know which coefficients are for which model, so I can do a tiny bit of processing. So I take my features no label to be this val, which is taking my data set, my original data set, and it's looking at the columns and then filtering them by this closure, which takes the column and then maps it to those that are not PE. So we'll get all the columns except the one we're trying to predict, right? So this is just a string, an array of strings. So, okay. Now what we're going to do is simply pair up the coefficient with the feature, right? So this is essentially a little trick. So I basically do sc.parallelize weights. And then I can do zip. Zip is just like a zipper, right? You can take two things and just zip it up. And I've done that, and what I'm getting now is just collecting that, and all that tells me is this coefficient belongs with this feature, and this coefficient belongs with this feature, and so on. And this is again, just let's sort the coefficients from the largest to the smallest, so we can see which has the highest. So AT has a very strong negative correlation. Remember, that's what we saw in the cloud of scatter plots, temperature. And then these other coefficients are closer to 0, right? So, so then we can just put our equation in this format that a lot of the analysts and other people can easily interpret. This is my sort of equation as a string now. Okay. Right, so once again, the atmospheric temperature has a very strong negative correlation, so there's nothing new. It looks like the dots we saw, and the other pairwise interactions are not as strong, so we don't really see a signal of this. Okay, so now we're going to just look at predictions and labels. So what we can do is use this transformer. So we can take LR model and transform it with the test set. So that means we can take the test set, plug it into the model, and get all the predictions in one go. So that's what is being done here. So we have our predictions. And so we have your power output and the predicted power output. So you can see, whatever, it's kind of off, but maybe not too far off, right? So this is just the fit from the linear regression. So this is, it's from 1, 2, 3, 4 dimensions, feature space. So now let's try to use some metrics. So we're going to compute some evaluation metrics against our test set. And for that, we load this evaluation regression metrics. And we're going to select from the data, from the predictions and labels data frame we just made here. We're going to select the predicted power output and the power output. And then we're going to turn that data frame into an RDD and then map each row via this closure, which is taking the first element of the row as instance of double and the second element of the row as instance of double. Right? So that's just these two columns. So now I just have the predicted thing and the actual response. So now I can compute the root mean square error, which basically is 4.68. So this is the square root of the mean of the squared errors between the prediction and the fitted model. Okay, and so Carl, can you maybe explain what explained variance is?
The R squared, yeah. So it's the.
Oh, this is R squared, but there's something else. Okay, this is R squared. Yeah. So yeah, go ahead.
So which one?
So there's something called R squared, and there's something called explained variance, right?
Don't know.
R squared is the ratio. R squared is the ratio.
Is the ratio.
Normalized, yeah.
Over the total. Yeah, the portion of the variance is explained over the total. Of
okay.
But not of the variances of the sum squares.
Okay, so this must be the numerator then.
Yeah, it is.
Yeah. Okay. So okay, so that's basically, and then you can sort of print this and see, how good the fit is. And now, so generally a good model will have 68% of predictions within one root mean square error and 95% within 2 RMSE of the actual value. So we can actually calculate this quickly, right? So let's display this, predictions and labels. So now we're seeing the whole table just to be sure. So here's my features as vectors and predicted power output. And So now what I've done is prediction and labels. I select expression P, predicted P, and P minus predicted P as my residual error. So this is all Spark SQL coming to help us. And then I'm basically taking P minus predicted P and divide by the RMSE as within root square mean error. And then I'm registering this as a temp table. Okay. So now this is going to give us, if we just select and display, we can now see what is the actual output and what's the predicted output, what's the residual error, and what's within residual error. So once again, you can ask, what is the distribution of within RMSE? And here it is, it's centered at 0, and it looks pretty tight. So now the question is the majority of the error within 2 root mean square errors? And to do that, we can just do this plot. And you notice that, yeah, most of them are within 1, and the remaining are 2 and 3. Okay, so about 70% of our training data is within 1 RMSE and about 98% within 2 RMSE. Now, what is tuning and evaluation? Tuning and evaluation, basically, we have to do a parameter grid, right? Because we have these hyperparameters we want to go over, and we have to have something called, the cross-validation method. Remember, we're going to hold out some of the data and use the training data to do cross-validation. So once again, this is done in parallel for you. So here's embed of the cross-validation method. So here's my reg eval, which basically is a regression evaluator. And then I'm going to set label column to be PE and set prediction column to be predicted PE. And then I'm going to set the metric name to be RMSE. Okay? So I need these things for my regression evaluator, which is going to evaluate the whole regression operation. So once I've done this, then I can create a cross-validator with 5-fold cross-validation. So it's going to take the data and actually do 5 folds of cross-validation. For each fold, it's going to do the validation. So this all is just about tuning, right? So, so here's my regression parameter. I'm going to make a tiny grid with regression parameter values from 0.01 to 0.1, okay? And this is essentially my, so remember this, when this value is 0, I'm in the L1 setting, and if it's 1, I'm in the L2, sorry, vice versa. And now I have my parameter grid, and I've actually taken the parameter grid builder, I've added the grid and built it. Now I have my cross-val set param estimator param grid, which basically is going to now allow my cross-validator to essentially go through all of this by caching what can be cached efficiently. Right? So this creates our model, our cross-validation model, and we can just call a fit on the cross-validation with the training set, and it's going to take a few seconds. And what in the end we will be able to do is, set up our CD model. There is another whole way of doing this. When the models get too complex, we cannot do cross-validation, so then you can just split the data into training and validation splits. So if you want to do that, you can chase that there. And here's our, so now what we're going to basically be doing is, so we've tuned, so let's see how good the tuning parameter is, and what our RMSE was for our initial model. So if we did this, we're finding that our actual improvement is not that much, right? Compared to what we did before. So all the extra hard work didn't really give us a lot more. So that's what this thing is saying. So which means a linear regression basically is not, you're not going to get a better fit by using linear regression, which means you may have to look at a different model. And this basically is regression trees. So we can set up the pipeline for decision trees that we did last week and take the entire data set, use parts of the pipeline from before, and now suddenly change the model of decision trees, right? So let's see how decision trees do, right? So once again, I can reuse my cross-validator and put the decision tree pipeline I just built. This is very similar to what we did last week, but for this power plant example. And then now I have my parameter grid set up. So here I'm only doing 2 levels, right? I only have depth 2, maximal depth 2, and maximal depth 3. And then when I do this, I have my decision tree model, and I'm doing cross-val fit training set, and I'm going through to the maximal depths of 2 and 3 over this 5-fold cross-validation, and I'm able to see how good my decision tree method is. So that's again, so I can look at what is the best instance of this decision tree, and I can just get this as a string, right? So if the feature 0 is less than 17.73, and if this is this, and so on, I'm going to predict this, right? So I'm basically, I've gotten a depth 3 tree with 15 nodes, okay? So that's, again, okay, but it's not ideal, right? So maybe I'll stop here. So what I wanted to maybe continue is later on from next week is, we'll just start from here. And what we can now do is actually gradient boosted trees, which will need some time. So I'll go through gradient boosted trees, what the basic idea is. And then with gradient boosted trees, we have an ensemble of trees, not just one tree, right? We'll have lots of trees. And when we do that, essentially we can, here's the code for it. And I won't run this because it's going to take, a few minutes to finish. I can do gradient boosted trees, and then I can find that my explanatory power, my predictive power is very, very high. And this is what we'll be using later on to do deployment. Okay, so I'll start from gradient boosted trees and maybe go slowly over cross-validation next week. Okay. And next week, after continuing on this, we will sort of get into Spark streaming, right? So again, this is very topical, but just to give you a flavor of all the various parts of MLlib. Once you get into Spark streaming, we can do deployment and we can start serving models to clients. Okay. Yeah, so there's a lot, right? But you can go back and clone and play. And so if you want, in-depth understanding, it's going to take time. And, are there any questions? I mean, those of you who are interested in research, right, like actually coming up with a better algorithm than what's in MLlib, my recommendation is first understand what's in MLlib, read the papers that are behind the algorithms, theoretical papers, and then you really need to go and nail all of this down, right? So you need to at least watch these videos and then start going through those 2 PDFs, the archive papers I linked. They're gone now. The archive paper of January 1, 2016 paper on distributed linear algebra and distributed optimization, and the reference papers. Then you will really start appreciating more, and I myself am learning. Okay, so I'm definitely not in a state of mind or whatever research caliber to be able to do new distributed algorithms and contribute to GitHub with the Apache Spark project. I'm not there. I'd like to be there maybe in a year or 2, but it's a lot of work. So learning what's already under the hood is actually a good first step, I think. Yeah, so maybe step 7 and 8, I'll repeat from next week. So does everyone who doesn't have a UC email address want Databricks Community Edition? Okay. Okay, good. Yep.